Hello everyone, my name is Claire. I am currently in machine learning and data mining master degree, and I did my internship on supervision GANs for bird imaging under the supervision of Yevgen Redko and Marc Sebon. The medical imaging is often in low resolution due to radiation exposure, slow scan speed, or limitation of materials. However, the resolution is a key issue. We know, for example, for the bones imaging, that in high resolution, the bones microstructure appear, and it's an important factor of bone stunts. So get the high resolution image from its low resolution counterpart is an important challenge. It will allow to detect better and sooner bones diseases like osteoporosis. The super resolution is a task to get an high resolution image from its low resolution counterpart. Since last year, the deep learning method was the state of the art. However, they are designed and trained on natural imaging, and we know that medical imaging have some particularities. They are all in grayscale, a lot of regularities. So the objective of this internship is to study, apply, and specialize the supervision methods SRGAN to mice bones dataset. SRGAN is a generative adversarial network designed for super resolution. Again, it's composed of two models, a generator who try to generate a convincing real image from a low resolution image, and a discriminator who try to predict if an image is real or fake. The both models are trained in same time, and it's a min-max program where the generator try to fool the discriminator, and where the discriminator try to learn to unmask the generator. The generator is composed of residual blocks. Inside there is convolutional blocks who learn feature maps. The feature maps are the weight of the convolutional layers, and it's what our model learn. And so the residual blocks try to extract the features the most important that contain the high frequency details, the most useful for the high resolution image. And at the end of the generator, we have the upscaling blocks who try to improve the resolution of the image using a sub-pixel convolutional layer who improves the resolution of the image from the output of the residual blocks. What we can see is with this method, we are a really convincing result. On the middle, we can see the output of our algorithm from the low resolution image at the left. And it's very close to the high resolution image, the green tooth on the right. In super resolution, to measure how much an image is good, we use PSNR and SSEM. It's metrics who are highly related with the mean square error. And for problem with natural image, we have each pixel of an image code information. But for medical imaging, we have a lot of black region. So these metrics are highly biased by the region of black pixel. So it's the first problem, and the second problem is because PSNR and SSEM try to measure how looks good seems a picture, but for medical imaging is not really what we want. So we also need to answer to the question how much the super resolution improves the reconstruction of the bones microstructure. To do that, we use a toolbox of biologists. The biologists, when they study bones microstructure, they compute a lot of parameters like the number of trabecular. The trabecular is the spongy bones, the bones inside the bones. And they compute the spacing between trabecular, the number of trabecular, and other parameters. So what we do is we compute all these parameters on the super resolution image, and we compare this medical parameter with the medical parameter of the high resolution image. Unlikely, it's what we do currently. So I can present the result now. But in parallel, we worked also on the large-scale factor learning. For a scale of factor 2 or 4, we saw just before the algorithm worked pretty well. But for high scale factor, it's failed to reconstruct a convincing image. It's probably due to the fact that the task is hard. And we can see on the diagram that the discriminator converged to 0 and the generator is not able to learn anything. Our hypothesis is the problem confirms the fact that the feature map of residual blocks have to extract all the detail from a very low resolution image, then improve in one step, then improve the resolution in only one step until the high resolution image. So, of course, in this context, the feature between low resolution image and high resolution image are far. So it's hard. And a first idea was to use intermediate representation. The idea is we have a block of residual blocks. We have a stack of residual blocks. Then we improve of 2 the resolution. Since the residual blocks learn only on the feature of low resolution and improve of only 2 and are only used to improve of 2 the resolution. And we do that again. So we have feature maps on each stack of residual blocks who are already specialized for only one step of one jump of resolution. Unlikely, we can see on the image that the super resolution image seems convincing because we can see they're close to the high resolution image, but we have a lot of hallucination. And to try to control that, we propose to add control on the intermediate representation. And to do that, we use a stacking of 2 GANs. So we have a first GAN who generate an intermediate representation, and discriminator who try to control if this intermediate representation is good or not, and another GAN who try to improve the resolution until the size of the high resolution image. However, again, we don't have convincing image. So in conclusion, we have good results for small scale factor. We measure the quality of the super resolution by using correlation with the green truth biological metrics of bone microstructure. But the super resolution for high scale factor is still a difficult challenge. And one of the great questions is how much we can improve the resolution, because for a factor of 8, we have 1 pixel in a low resolution image who correspond to 64 pixels in high resolution. So it's definitely a very hard task, and we don't know how much we can reconstruct the high resolution image. Thank you for your attention.